reference systems. I mean, many of you probably already familiar with Earth-based reference systems, some of you not. The planetary one are very similar, but of course there are differences. And I will try to highlight some of them, and you will see many more of them than in practice in the next few hours. Basically, first of all, there are many reference systems and many reference frames, and both in space and time. And when we are thinking of mapping, we have to consider that we are at the end of a very long pipeline of thinking where to go on the solar system, when to get into orbit, what to look with a certain pointing, at what time, because of course, your satellite is moving if it's orbiting a planet, and if you want to image a certain area, it takes a certain moment when you're pointing at a certain direction. All of it is extremely complex, and fortunately for us, is taken care of by the people who are taking care of the experiment development and imaging planning of any instrument. So it's transparent, but it's there. And all these reference frames have to be considered when we get to the mapping itself. At the end of the day, what we want to do is to look at the picture on the right and then start mapping on it. That's what we will do. But before we get there, we have to get the individual data products together, mosaiced in common projections. We'll get to it in a moment. And obviously, this means that you have to take it from a spacecraft. All of it is very complex, and there is a lot of resources that we have no time to go through in this week. But if you want to get into that, there is a lot of material and an extremely rich amount of documentation. And then there is an issue that on Earth you also face, but a bit less, which is the accuracy, which is also the result of a long chain of possible errors and inaccuracies that are just simply related to time or to the detail to which you know the certain position of a spacecraft in time. There are ways to deal with it, for example, doing bundle adjustments, all sorts of control mosaicing, but obviously that's something that you have to consider. And you will see it in practice. We left some of the data not really completely well registered. You will see it, for example, in the Martian zone. So that's one of the things to be considered. Plus, typically with GIS, in general, mapping or geospatial data, there is a lot of definitions. Some of them are very complex. At the end of the day, try to sum it up. A map projection is a way to represent, is a representation of a model of your surface. And the CRS is something that also considers or is embedding the reference body you have. Maybe a sphere, maybe a spheroid, maybe a geoid, maybe a very complex shape model. At the end of the day, all we do, it's computer-based, but it's not so much different from what you do by hand. It's simply implementing via algorithms and software what you will do with hand, pen, paper, and math. And at the end of the day, what we are looking at, and you will hear more about that with Riccardo in half an hour or less, it's geospatial data that can be already digital or can be made digital later on, for example, scanning them or digitizing them. That's the case, for example, for early planetary data. Now, the reference surfaces or bodies can be very different, and you will see that what we're going to do this week is mostly with very simplified reference bodies, which are not even ellipsoidal, actually spheres. There can be a wide range of both vertical and horizontal reference systems, but typically spheroids are used for maps for their simplicity, also mathematically. And map projections are a way to actually transform, more or less, you are doing dimensionality reduction. You're transforming from a 3D problem to a 2D problem in general. So you're projecting the surface of something that is not two-dimensional into a two-dimensional piece of paper or screen. And obviously, you need some kind of coordinates to use. They can be Cartesian coordinates, X and Y, or they can be angular coordinates, like latitude and longitude. Typically, most of the things that we do, and you will do also next days, are using metric coordinates, which are Cartesian. So at some point, you have to transfer from the latitude and longitude angle to the X and Y. And that's all about GIS operations. Of course, there are many classes of projections depending on on the shape of the family of shapes that you can choose to plot these maps from the 3D body to the 2D representation. And depending on which kind of surface you use, you can have all range of cylindrical, conical, and azimuthal projection. And you can mix and match transverse, oblique, or simple projection. So you can essentially have a wide range of variation of this kind of envelope that is displayed here. Now, that's the same also for the latitude. Typically, you are having in planetary data or planetary mapping 2 types of latitude, and this can also cause confusion since decades. We are going to try to sort out this confusion with some, well, not really a trick, but some simplification. And effectively, depending if you consider the angle between the intercept of the point on the surface and the center of your ellipsoid, you have a planetocentric latitude, so to say. If instead you consider the normal to the point intersecting the equator, it's a planetographic or planetodetic. But at the end of the day, we want to simplify also for other reasons, technical ones. And so if you're using a sphere, not a spheroid, an ellipsoid as a reference surface, of course, the 2 angles are the same. So more or less, you can just consider that the planetocentric and the planetographic latitudes are the same. Now, why I mention this, because these are practical things that you will encounter. And you have to be aware when you get data and you integrate them yourself, you may face issues depending on this. Now, back to the map projections, there are certain things that are important to consider whether your map projection, which is, again, an approximation, it's a model, is respecting, and if not, to which extent, the maintaining some of the parameters. For example, if you're measuring the areas of crops, you want to make sure that your map projection is equal area. So, which means that the areas you project on you map on the projection is the real one that you will have on the surface. Same for the angle. If you're navigating and you have only a compass, you want to make sure that your projection is conformal, so it's keeping the angle. And if you're looking at distances because you're doing some kind of analysis of how to better organize the shipping of goods, and you have to see how much gasoline you're expending with your trucks, or electricity, you better use an equidistant projection. So this can be tricky, and several projections have different characteristics. So the point is that you have to look up and see what can be more suitable for your needs. The good thing is that there is some resources, and if you have time, I will go through with you. So you are not alone in that, but obviously it's something that you have to think about when you're choosing a projection, or when someone is giving you data in a certain projection, whether this is suitable for the work you want to do or not. Now there is a thing, there is many things that projection can do or can offer in terms of features or problems. And one is distortion. And what you see here, this kind of yellow things, they are like circles in some parts of the map, and they are very, very deformed. There's ellipses somewhere. These are the so-called Tissot anticatrix. And it's just a mathematical way to define and to show, to visualize how much there is deformation. There is a very good thing is that planets, typically and moons, they have this kind of indicatrix for free. And it's actually made by craters. You will hear by Caroline tomorrow about that. But most of the craters are actually round by nature, which means that if you see things that are not round, well, probably here is to blame at the projection level, right? And in fact, you see, it's funny, the yellow bits are showing consistent deformation where the craters, this kind of depressions that are roundish, are not roundish anymore. And we can move on. These are other examples of projection. It's also cylindrical, so where the envelope, it's a cylinder touching your reference body. And you see that the aspect ratio is a bit different, and so is the deformation. It's extremely high, close to the higher latitude, and then is relatively low across all longitudes. Same story with another projection, the sinusoidal. We'll get back to it in a moment later. You see that when you're close to this meridian, so these vertical lines of a certain longitude, which is at the center, you notice two things. One that is straight, and the other one is that these kind of roundish things are quite round, which means that the deformation along the central meridian is not so much. And if you move to the left and to the north, they are getting very squeezed. So this is one of the things that you should consider, that whenever you choose a projection, typically the distortion and the fidelity of the projection is highest when you're closest to the center of it. That's why, for example, on Earth, we're using universal transverse Mercator, and there are many fuses of them, because each of them is quite good in the vicinity of its center. This also brings 2 points. One, that the projection depends on your application and also the scale of it, if it's local, if it's regional, if it's global. First one. And the second one is that some projection just cannot handle global data. For example, if you look at the orthographic, which is not so different from the way we see the moon in the night, well, you will never be able to see the backside of the moon from where you sit. That's why you need to have spacecrafts. So when you have all these things in mind, you should consider that each projection has assets and problems, and depending on what you do, it can be acceptable or not, but can be tricky at some point. That's an example of using the very same projection, a conformal, which means that the angle, so the direction of things is like in the real thing, just globally or half globally, spherically, and then on a small subset. You see that Europe and Africa are not too bad, and also North and South America are not too bad. But you start seeing that although the shape of Greenland is quite good, it's big. You see it for 2 reasons. One, because you know that the Greenland is not as big as all Europe, and the other one, because you have the indicatrix that is just confirming that for you. Now, how do you choose the projections? First of all, there are like entire books, literally, on this topic. Actually, you will provide, I have links to them. But basically, there is some guidance, and depending you're working, apart from the parameters that you want to consider, angle, distance, or area, if you want to work on small scale or large scale areas, regional or global mapping or very local mapping, different projections, they can have different role. So there are resources, like there's another book, but I will point you in a moment to other ones when we move on. And this is just an example which gives you the idea why, how we deal with the regional maps on planets or moons. And you see that on the bottom left, you see it's all squares or rectangles. Well, actually, that's misleading. This is simply the way it's divided. But the way the actual maps are projected is like on the top left or the bottom right. You see there are rectangles close to the equator, so -20 to +20. Actually, these are in cylindrical equidistant projections typically, so they're like the first one you saw. And then you have this kind of curved upper and lower bounds. These are typically conical projection. You see, it doesn't look so much different from this when the parallels are curved. And obviously, you have this kind of round bits on the south and north. Well, actually, these are the so-called polar stereographic that you will see in a moment. So all of it, actually, they are important, and all of them are used. But depending on where you are, you may want to use one or the other. Very quickly, 2 concepts. One, the fact that projections are most faithful to the reality at the center of their central longitude or latitude. And this is just comparing very quickly. This is just a zoom of it. A cylindrical, equidistant, and an orthographic. So the moon, like you will see it from Earth. Now, the white dot is the center of the latitude and longitude, so 0, 0. And now we play a bit on and off. You see that at the center, there is a bit of moving around, but not so much. This means that, of course, the orthographic and the cylindrical, although they are very different projections, they are not too far from each other in terms of scale at the center. But you see, when you move to the side, it's getting tricky. And basically, this tells you 2 stories. One, that the deformation is higher at the sides. And the second one is that, for example, with the orthographic, as we said, you cannot image an entire planet with an orthographic projection. You need at least two of them, from one hemisphere and the other hemisphere. And then basically, if this green area is effectively this. What is missing, which is again another half more or less, it's again the far side of the moon. And then we can move on like that. On top of it, depending on if you're working regionally or locally, you may have different issues. For example, you see this square here, that's an image map that is in a certain area of the moon. Well, those are all the same area, but with different projections. And some of them, you see, they're rotating, they're upside down, some of them are squeezed. Depending on the projection, you may keep the area, but you may really destroy your geometry. And depending on which kind of geology or things you map, or if you're doing quantitative measurements like crater counting, you will hear also tomorrow, this can be critical. These are just examples, and you will have access to all of them, of how different projection, like simple degrees of latitude and longitude, or the metric version of it, which is cylindrical equidistant, can affect the geometry. Remember, the craters are your Tissot indicators for free. So the rims of the craters, which are red here, they are actually your proxy of the formation. And the lila one actually are the maria on the moon, so the basaltic lowlands you will hear also on Wednesday. And these are also a proxy of the surface, just for you to have a look. The crosses are each 10 degrees. So it's a proxy of the difference in latitude and longitude. Now you see, moving from a cylindrical equidistant to an equal area cylindrical or to orthographic, you see different things. First of all, that the apparent size of things can change, and also that while here the crosses, which means that the degrees of latitude and longitude are equally spaced, here they are not. They are kind of similar at the center, but we saw it before. And when you move to the edge, they're getting closer and closer. And of course, some of them, half of them are missing, so you need two of them. Same story with the stereographic, which also is an azimuthal projection. So you have a kind of a plane projected close to the pole of your body. You see that they are very close to the center, and then they're getting very far, extremely far. Now, you remember the lila stuff. The lila stuff are the Maria. So it's kind of a 1/3, half of the moon when you see it at night. It's big. And now look, there are craters that are looking like tens of times bigger. Is this realistic? No, it's not. And that's exactly the point, is that when you're closest to the center of a stereographic, you are not too far off from the real scale. When you're moving away, you have still a nice geometry because the shape is still round, but things are getting really expanded. And same story here with the South Pole, or here of the North Pole. Remember that all these things are, of course, of a limited known size, and depending on how you play with the projection, this can cause deformation that may be misleading for you. So that's how it looks like. So you see, essentially, it's half of the moon is the lila stuff. And depending on the way you project data, you may end up underestimating or overestimating areas, distancing, or misestimating angles, which means shape. Typically, a projection where a crater is very squeezed means that it doesn't respect angle or shape. Now you see there is a scale bar. If I exaggerate it too much and I start to put the scale bar, I get some small craters on the moon that are like 5,000 kilometers wide in size. Is it realistic? No, obviously. The real size of the moon is like with a radius of 1,700 kilometers, so it's really tiny. And obviously, these are all artifacts of the projection. But if you're very close to the center, you're pretty good, and the scale is not too bad. This is the same story of why the Mercator projection is very good, because it's keeping the angles and the shapes, but it's very bad if you're looking at the scale of things. And that's why you get Greenland, which is as big, if not bigger, than Africa, which obviously is a deformation. Back to the sinusoidal. Also, the sinusoidal we introduced before, it has very little deformation at the center. And sometimes either your map in a certain way or your products that you want to use for a map are pre-projected. This is actually the case for HRSC, which is an image you will learn in half an hour from now by Ricardo. This data, they can have their own projection. And sometimes you have to change it if you want to do your mapping. Obviously, in this exercise for the school, we have everything pre-cooked for you. But in real life, you will have to cook yourself your meal with the data. So you have always to consider it. Just an experiment. This is one single image that you see on the left. It's over Olympus Mons. You will hear about that on Thursday. That's an equirectangular projection. So you can see that the deformation at low latitudes is not so much. Things are round. When you move to the south, they're getting very squeezed. If we do the very same thing, sorry, I didn't want to open the, apologies. If you do the very same thing with the sinusoidal projection and you're centering it at the 0, 0, so to say, at the normal way you will do it, well, the deformation is extreme, and both the touchless area you will get no, and the image are very squeezed. But of course, I can have a trick, and I can just choose or tell the projection to be centered at a certain longitude, so at a certain meridian. And you see that here the deformation is very little, which means that the shape, of course, the area is preserved in the sinusoidal, but even the shape is pretty good and is not too far from the real thing. So I suggest you very warmly to go through these two videos, which are a bit old, but I think they are very good to introduce both the concept of cartography and GIS, and also the historical aspect, particularly the first by Stefan, but also the one by Trent. And Trent will also speak to you later in the afternoon, why products and many cartographic background work, it's important for geology. Because as Matteo was saying, in order to map, you need to have some knowledge of the surface. And the knowledge of the surface comes from data and, of course, from your coordinate reference system that helps you to put together the data, together with many other things. I also had some references here that are also on the repo, and most of it, I would like you to have a look here. There is quite a lot of references. Again, some of you may not need them because you already are fluent with this, but please have a look, go through it. There is very much free and good quality documentation around. So this should help you very much to get acquainted with map projections and eventual tools. On top of it, the slides that you just saw, they are already on the webpage of the school here under the contribution. So you can have both access to the PDF and you have access to the repo that I just showed you. We have a few minutes, so if you have any questions, maybe we can discuss it here. And please feel free to also ask on Discord later on. Thank you, everyone.